Welcome back. In this one, we are going to take a break from digesting large amounts of information and just sort of fool around a little bit. And what we're going to do is take a look at two programs that max out CPU and another one that maxes out memory. These programs or scripts serve no functional purpose really. They're just fun. Or at least I think they are, because they just kind of demonstrate and drive home the fact that you can write a program that does almost anything you want, and depending on the OS and sort of the way that it's set up, it may or may not stop you from doing insane things, and that's always fun to mess around with, or at least I think it is. So again, the first one we're going to mess with is the CPU one, and basically my laptop runs it's a quad core system, and it has virtualization and stuff like that, hyper-threading and stuff. So it has 8 logical processors, and if we just had one, like a uniprocessor system, we wouldn't have any problem writing this. It would be 3 lines, or maybe 4. I don't know. It'd be somewhere around there, and it would be very easy for us to write something that would just peg that one core, or that one processor. But it's a little trickier when you have multiple cores / multiple processors, because you have to sort of structure it in a way where it will have enough work to pass around to the different processors. So if we used the version that would peg a single core system or single processor system, what we'd find, if we ran that on this system, what we would find is that it would do, like 10-15%, something like that, somewhere in that range, worth of damage to the total CPU capacity, if you will, of the system. So I ended up having to rework it a little bit, and was able to achieve the desired effect, which is CPU pegging for across all the processors, physical or logical. So for this, what we're going to need is conemu, because we have to be able to run the commands from somewhere. And then we're going to start up Task Manager, and then from Task Manager we are going to go to Performance and then open the Resource Monitor. Might be a little different if you run Windows 7, but I have confidence that if you click around in the Task Manager, I'm sure you'll be able to find the Resource Monitor. And if for whatever reason you can't, just go to the Start menu and poke around in like Administrative Tools or Performance or something like that, and you'd probably be able to find it. You can just search for it, I'm sure. So Resource Monitor is probably what you'd look for. So if we look at Task Manager, the CPU is just sort of humming along nicely. It's not crazy. And if we go over to the Resource Monitor, we can scroll down and see CPU 0, 1, 2, 3. They're not doing much. CPU 0 seems to be doing some stuff. 2 is doing a little bit. The rest of them are kind of... 6 had a little spike there. 7 appears to be doing something. But overall, the general system load is not that high at all. So let's see if we can change this. So I'm going to sort this by CPU. I'm going to go over to details and just make sure I have this sorted by CPU as well. The system idle process will almost always be on top. But anyway, I will navigate to this directory. And in order to run this, it's a Python program, so I have to run it through Python. So I will just do that. And all things being equal, when I hit enter, what we'll see is in Task Manager over here in the upper right, CPU will jump to 100, and then all the cores over here will get pegged to 100 as well. So we're generating enough work for all the for the OS scheduler to delegate tasks to all the different processors, and we have enough work for it to delegate so much work that it will peg them all to 100%. So let's just go ahead and run it, and we'll see this instantly jump up to 100. And we'll give it a second. It'll start to refresh and draw over here. And the CPU totals at 100, or certainly really close. And if we scroll down, we can see that all the cores are in fact pegged at 100 as well. So that's kind of fun. And again, if you had just one CPU or one processor, writing the program would be a lot easier. You could just make it count to not even count, because it'll eventually get there, but you could just write a simple loop and just have it spin. But having multiple processors present on the system presents a somewhat more unique challenge. So let's go ahead and stop this. And we can hit Control C, but it doesn't seem to... Does it actually kill it? It seems like it is sort of calming down. Yep. So it does seem like it calmed down quite a bit. Reduced sort of normal load. We can hit Control C again, try and get out of it. And Python's eventually going to crash. And it gets pretty messy pretty quick. And we can see we still have a whole lot of Python processes over here, although they all have a status of terminated. So if we go over to details and sort by name, we can look for Python. We can see there's still a bunch of them running. They may be in the terminated status, but there's still a bunch there. So the easiest way to do this is going to be to close whatever console you use to open this stuff in. So we're going to go ahead and create a new console because I want to be able to leave con emu up. So what we're going to do, if we close this this particular command prompt, it's going to terminate everything that started from it. And don't worry about all this garbage here. At some point we'll be able to read all this, but at this point it's just garbage. So we're going to close this tab, and it's saying, hey, I still have stuff running inside of me. Are you sure you want to close this? Because I'm going to end up killing most of that stuff. We're going to hit yes, and all that stuff goes away. So we'll go ahead and sort by CPU again. See the idle process is about back to where it was before, 93, 92, 95, something like that. So, again, that was kind of interesting. So we will open up Sublime, which is what I used to write it. And this is essentially the 9-line program, 10 if you count the end line, that pretty much pegs all your processors. So we'll go through it a little bit. I don't want to get too bogged down on the details, but multiprocessing, we're going to import something called pool, and multiprocessing is essentially a built-in part of Python that you can use to distribute work across multiple processors. So basically it allows you to parallelize things across multiple processors. And then what we have here is a function, which we'll talk all about those, I'm sure. But the important part is this, and basically what this is saying is we are just going to, true is always going to be true. Because true is an artifact, not artifact, but it's a part of Boolean logic, and it just represents something that it is true. And because true will always be true in the context of a computer, I realize that's kind of meta, but just bear with me, we are going to do nothing. And so pass is just a command to Python that just says, just skip it. Just do no work and go back to whatever you were doing. In which case it's going to go back up to while true, and it's going to go back down here, and it's going to do nothing, and it's going to go back to while true, and it's going to go back and do nothing, and it just spins in this endless loop at maximum frequency, if you will, because there's no sort of checks built in here. We're just saying, do this loop that has no work inside it, do this as fast as you can, and never stop. We're not going to worry about this line too much, but there is some purpose to that. We'll get to that once we start looking at Python. So the next thing we're going to do is create a pool, and a pool is a way where you can delegate work from the multiprocessing part of Python. Basically, when you're creating a pool, you're essentially telling Python, I'm going to give you work, and I want you to handle it behind the scenes, and I want you to just spread this work over as many processors as there are in the system. So when you create a pool, it defaults to, it'll actually go to your system and say like, hey, how many processors do you have? And the system will come back and say, well, I have 4 or 8, as the case in my laptop. But and then pool says, okay, cool, and it sort of like initializes itself to, okay, I'm going to spread work across this many processors. And then the map function, or method, if you will, basically what we're saying with this line right here is we're telling the pool to call this function f, and then the way that the map function is constructed, you have to actually pass it arguments. We're not going to worry too much about that, but basically I just generate some arguments, just a list of numbers, and we can evidence or see the fact that I don't care what the arguments are, because the argument to this function I just call dummy, and I don't do anything with it. So just by virtue of calling the map function, it's going to delegate f to 8 processors, or as many processors as are in the system, and each processor is just going to enter this and start spinning and spinning and spinning and spinning, and we saw the results of that. So I don't know, it's kind of fun. It's interesting. And there's way more practical applications of this in a real application, but or a real program, but I think it's interesting. So the next one we're going to do is this memory one. And this memory one's a little more interesting in the sense that we will see some strange results. It'll be a little more well-behaved than the CPU one in the sense of like killing it will be a little easier. As a matter of fact, it's going to kill itself, and we'll talk about why in just 1 second. But what we're going to do is switch down to the memory, and we'll change the sorting on the details over here to be memory. So we're going to end up running this a couple times, but we'll just watch performance first. So we're going to go ahead and run this, and we'll see the memory start to spike up, and then eventually we're going to get the memory error, and it's going to drop back down. And we'll go over to we got, what was that? It was like probably 1.5 gigs, 2 gigs, something like that. So we'll go over to details, and we have it sorted by memory. So we're just going to go ahead and run this again and see what we see over here. So it's got 1.6, 1.9, 1. Almost 2. It gets a memory error, releases all its memory, and dies. And we'll just run that one more time. 0.5 gig, 1.8 gigs, almost 2 gigs, almost 2 gigs, almost 2 more. It's dead. So what's going on here? Shouldn't we be able to write something that just chews up all the memory in the system? And the short answer is yes and no. The short answer is, yeah, you could probably write something that would get around this. It has something to do with 32-bit versus 64-bit. But what's really going on here is that 32-bit processors have a limit to the amount of memory that they can access. So because it's 32-bit and memory addresses are essentially 32-bit for a 32-bit process, as it's trying to allocate memory and write things into memory, which is what our program's trying to do, it's essentially just requesting memory nonstop, and it's writing garbage data into that memory. What we're seeing is that once it gets to that 2 gig mark, Windows with a 32-bit, I have 64-bit version of Windows, but with a 32-bit process running on Windows 8, 64-bit, essentially has a hard cap on how much memory a 32-bit process can run, because it reserves part of it for itself and virtual memory and stuff like that. All kinds of weird memory management details, and you can actually see what the limits are. If I want to say you go like memory limits, Windows, for Windows releases. So if search for that, you'll get this article. I believe this is the one. Memory limits for Windows and Windows Server releases. So what we're doing is using a user mode virtual address space for each 32-bit process. This is what we want to pay attention to. And the limit in 64-bit Windows is 2 gigs. Or if we enabled this thing, which is we're not going to get into, but we'd be able to jump up to 4. But essentially, we're never going to be able to get beyond 2 gigs memory. And so that's essentially what's going on here. Is it's just once we get to that cap, Windows is just like, you have no more. I'm not giving you any more memory. Stop asking me. And the process keeps asking it, and Windows just says, I'm done with you. And essentially, you just Python, or the OS tells Python that, hey, you're out of memory. Python, and then another request comes in, and another request comes in, and eventually Python itself just goes back to your script or your program and just says, I got nothing else for you, and it throws this memory error, and it just dies. And essentially it just kills it. So with a little ingenuity, we might be able to get around it, but we'll go ahead and just look at it. And so we said we weren't really going to worry about this line, and I'm not really going to worry about it in this one either, but let's look at what we're doing. We're essentially making a variable, and it's what's called a list. And basically a list is just, think of like a bullet point list. So you have like bullet point 1, you have bullet point 2, you have bullet point 3, and then you have some arbitrary information on the first bullet point, the second bullet point, the third bullet point. Lists are very much like that. We'll go through the actual, what's called like the data structure of a list at a later date, but we notice the while true here as well. So we're essentially just saying don't ever stop doing this, because true is always true. So just keep running this loop as long as you can. And what we're doing is we're appending information onto this list. So to use our bullet point analogy, if you made a bullet point list and you had 5 items in it, and then you suddenly wanted to add a 6th, you could just be like bullet point or bullet list append, and then just throw some random information on there, and then it would just add a 6th point and then a 7th point. So we're essentially growing this list by an amount equal to the letter X times 1024. So I used 1024 just to get kind of close to like, this is not actually, most characters, or traditionally, characters are 1 byte. Python's a little different, but which is to say that one letter in Python is not 1 byte. It's actually quite a bit more. I believe it's like 25 or 26. The reasons why is kind of complicated, but they're not really worth diving into right now. But I just used 1024 because it's a nice, kilobyte, megabyte, stuff like that. So we just keep making this list bigger and bigger and bigger until it hits 2 gigs, which is ridiculous for a list. And then it just dies. And then again, we get the memory error. We can maybe fool around with this a little bit and do like a, is it going to be that? We could do like, I'm not sure if that's going to do what I think it's going to do, but we'll go ahead and try that. So there's the size of our list, and it's just getting bigger and bigger and bigger as we just stuff more and more data into it. And if we go to performance and memory, it's probably going to get killed at some point. Memory. Where's my Python? So adding the print statement may not have been the best idea, just because it generates I/O, which is really slow. So just by virtue of being really slow, you can see it's still growing, but it's just not growing as fast as as it was before, because it has to take time to do all this I/O to the monitor and the console and stuff like that. So we're going to just go ahead and kill that if possible. So we kill it, it goes away. We'll go ahead and get rid of that. But if you wanted to, and you wanted to just generate tons of, or consume tons of memory at one time, you could probably just add another thing like that. And if we run it now, it'll probably just die in like a second. So that was fast. So basically, it just probably pulled like a full gig, and then it goes to get the 2nd gig, and just the same sort of process. The OS tells Python you're done. The Python tells our script that it's done, and then it just dies. So, and that's 4 lines of code. There's probably a more efficient way to do this, but this is just how I chose to do it. So at about 9-10 lines, we can max our CPU with as many cores as we have, or processors as we have in our system. And with 4 lines, maybe 5, if you count the blank one that I usually put at the end of source code, you can chew up as much memory as the OS will give you. And depending on whether your process is 32-bit or 64-bit, is going to determine how much memory you can chew up. If we could somehow start a 64-bit Python process, we could probably blow away all the memory in the system. Because I think there's only 8 gigs in this machine, and I think that the limit for 64-bit is 8 gigs. Limit in x86 not applicable. x64 is 8 terabytes. So yeah, I'm confident if we were able to spawn a 64-bit Python process, we would chew up all the memory in the system. And the reason why we don't is just because I happen to install a 32-bit version of Python. At some point, maybe I'll rectify that, but it's not really that important right now. So we'll go ahead and just close this down. That should be the end of this demo. I don't know, I was fooling around a little bit. It's better than sitting around reading Wikipedia nonstop. It's a little more interactive, I suppose. Demonstrates some of the ability that you have and just the power and control that you have over your system, even in a high-level language like Python. And you could write that same program probably in any programming language. Certainly you could do it in C. I know I've done it in C. All the way up to Python. You could definitely write it in Java. You could probably write it in JavaScript. I don't know why you'd want to, because JavaScript's generally like a client-side web browser language thing, but if you really wanted to, you could. But that's gonna pretty much do it for this one, and maybe we'll mess around and I'll think of some other quasi interesting thing to do. But at this point, I think we've gone as far as we're gonna go.